In this video, we're going to illustrate how the limit comparison test can be used to determine whether the series converges or diverges. Let's start with this example. So we have the series as n goes 1 from infinity of n squared plus n plus 1 over n to the fourth power plus n squared. According to the limit comparison test, what we need to do, we need to set up the following limit. Limit as n approaches infinity. And this limit is applied to the quotient such that in the numerator we have the general term of our series. We call it a sub n. So that is a sub n. And in the denominator we use the general term of the different series. And if we find that this limit is equal to a finite positive number, then either both of them converge or both of them diverge. So when we use the limit comparison test, our goal is to find such series so that we first of all know whether it converges or diverges. And then second, so that when we put its general term here in the denominator and simplify all that, we can find the limit somewhat easily. And also that limit is a finite positive number. So that's our goal. Now the easiest series to work with are p-series, and that's the one we're going to use. We know that the p-series comes in the form 1 over n raised to a certain power. So it's going to have this form. N goes from 1 to infinity, 1 over n, and then we have to use certain power. So here's the question, what power to use? This is how we're going to think about it. Once we put this general term, that's b sub n, in the denominator and simplify this all together, we want to obtain expression for which it's easy for us to obtain the limit. And we know that when we work with rational expressions like that, we can find limit very quickly when degrees of the numerator and denominator are the same. So if degree of the denominator is 4, I want to have same degree in the numerator. Well, right now it's degree 2. So that makes me to realize that I have to use power 2 right here for this p-series. Let's see what happens when we put them together. So we know that in the numerator we're going to have n squared plus n plus 1 over n to the fourth power plus n squared. That's the numerator. And in the denominator we're using 1 over n squared. So that's b sub n. Okay, well, to simplify this complex fraction, we'll just have to take expression from the numerator, or fraction from the numerator, and multiply it by the reciprocal of the denominator, so it's n squared over 1. Then we'll multiply the denominators, nothing happens, right? Nothing changes. In the numerator, as we multiply the numerators, well, we will be distributing n squared, and see how the degree of the numerator becomes 4. So it's n to the fourth power plus n cubed plus n squared over n to the fourth plus n squared. And I'm using the shortcut here. I know that, once again, if the degrees are the same, this limit will be equal to the quotient of the leading coefficient. So the leading coefficient here is 1. The leading coefficient in the denominator is also 1. So it's 1 over 1, which is 1. That is a positive number, finite number that's greater than 0. Okay, so we got the result that we wanted, but what's the conclusion here? Is our series divergent or convergent? Well, it all depends on this series that had b sub n. Is the series convergent or divergent? Well, it's a p-series, right? That is a p-series with p power equals 2. And we know whenever power is greater than 1, then the series is convergent. So therefore, converges. And now, since this series converges, then our series converges as well. According to the limit comparison test, if we get this limit to be a finite positive number, then both of them either diverge or converge. Since this series converges, our series converges as well. So converges by the limit comparison test. Okay, so we're going to do one more example. So let's try to determine if this series converges or diverges, series of e to the power 1 over n over n. We're going to apply the limit comparison test. So I need to find a series such that when I take this general term and put it together with the general term of this new series in the quotient, I have a limit that equals to a finite number. So according to the limit comparison test, I will have to set up the following limit. So I'll have to take the general term of my series, of the given series, it's e to the power 1 over n, and divide it by the general term of another series, for which I know whether it converges or diverges. Well, and as I start thinking about what I have here, I can see that if I can cancel n here in the denominator, I actually will be able to take limit of e to the power 1 over n, right? So as n approaches infinity, this power, so the denominator approaches infinity, so it means that the power approaches 0, and I know that e to the power 0 is 1. Yeah, so canceling that n will do it for me. So by what do I need to divide to cancel this n? Well, I have to divide by 1 over n, right? So that becomes limit as n approaches infinity, e to the power 1 over n times the reciprocal of the denominator, n over 1. So I can divide out n's, and here I'll get limit as n approaches infinity of e to the power 1 over n. Now, once again, as n approaches infinity, as the denominator of this fraction approaches infinity, the fraction itself approaches 0. So what I get is e to the power 0, and now anything to power 0 is 1. So in this case, once again, I got finite number, and that is positive, greater than 0. So I will be able to say whether my series converges or diverges once I figure out if series containing this general term convergent or divergent. Let's look at it. So that's going to be p series, right? That's a p series. Power equals 1. Well, we know when power is less than or equal to 1, we have the equal case this time. We know that in this case, the p series diverges. And since the second series diverges, our series diverges as well, according to the limit comparison test. Either both of them converge or both of them diverge. So since that one diverges, our series diverges as well. Diverges by the limit comparison test. Okay, so that's how we use the limit comparison test.